Okay, so good evening, everyone. Uh, the topic of our presentation is the deep learning model for anomaly detection. We are a group of three people: Abhishek Jangir, Sujay Verma, and myself, Shavik Bhattacharya. Recent applications of convolutional neural network have shown promises of convolutional layers for object detection and recognition, especially of images. However, convolutional neural network are supervised and require labels as learning signals. We use a spatiotemporal architecture for anomaly detection of videos, including of crowded scenes. And the architecture basically includes two components: one for spatial feature representation and one for learning the temporal evolution of the spatial features. And the further detail of the architecture would be explained by Abhishek. So I'll be moving ahead with the pre-processing part of the code. For the dataset, we are using the Avenue dataset, and it basically contains uh, the training videos and testing videos, and we have approximately 16 training videos and 21 testing videos. So what we are doing is that we are extracting 5 frames of each videos, and we are creating a bunch of functions for pre-processing. This is the create directory function, which is basically used to create the directory for storing the extracted frames of the videos. And the remove old images function is, as the name suggests, is used to remove the old images. So suppose if you are training it multiple times, so the every time the older images would be removed with the help of this function. And the third one is the store function, which is used to store the images. First of all, it is converted from image to array, and then it is stored. Then the image is converted into NP array, and it is resized to 227 cross 227 cross 3, which is coherent with the input shape of the network architecture. And then we are grayscaling the images, and we are appending those images into a list called image store. So first of all, we are extracting the directory of the videos, and then we are calling the video above mentioned functions. And then what we are doing is that for every frame of the video, we are changing it into a numpy array, and we are simply appending it to a list. So then what we are doing is that we are normalizing those images, and finally we are using np.clip to uh, clip the pixel size within these two ranges, that is 0 to 1. And then we are saving this into training1.npy, which will be used to in the training phase of this architecture. So next I would like to call upon, let me first run this code. So after running this code, we will be provided with the training1.npy, which will be used to okay. So as we can see that this file is getting created. So this was my part, and for the next part I would like to call upon Abhishek Jangir.
Thank you, Shavik, for briefly explaining what is the model and what dataset we are using and the processing part. Now, I would like to continue with the training part. So, as we know that by using process.py, a training.npy file is getting created using the training videos of our Avenue dataset. And now using this training.npy file, we are training our model. So first of all, I would like to talk about our model. So I am using training.npy file in our Google Colab to train our model. So as we can see that our network architecture contains initially it contains a convolution layer. So here we can see that we are using Keras layers, uh, and then we are adding a layer of 128 filters and stride 4 with the kernel size of 11 into 11. And after that, the second special encoder layer is getting created, which is this one with filter 64. And after that, we are adding some convolution LSTM 2D layers which are used in this temporal encoder decoder. As we can see here, we have three convolutional LSTM layers of kernel size 3 into 3 and filter size 64, 32, and 64. So here we can see that we have filters of 64, 32, and 64. And after that, we have a special decoder in which we are using the deconvolution layers with filters 128 here and kernel size 5 into 5, and also the last layer is also a deconvolution layers with filter size 1 and stride 4 and kernel size 11 into 11. So after that, when we pass a video to numpy array like video to this architecture, then we get a nearly reconstructed same output as the input from this network architecture. And then we compute the loss between the our input and our output, and if that particular loss is greater than some threshold, then we say that our video is anomalous. So before going on our testing, now I would like to talk about our training. So after creating the model, what we are doing is we are using the our numpy file which we have taken from our process.py file. And after that, because we want our frames to be multiple of 10, because of that we are using this line of code to make it multiple of 10, and then we are reshaping our input so that we can pass it in our model. And we are training our architecture for like 100 epochs and with the batch size 1. So we are using sgd for training. And after that, we are also creating some early stopping criteria on validation loss. And after loading our model, we are fitting our model on X training and Y training data with the pair size 1 and 100 epochs. So this is the training. So as we can see, we have trained it for 100 epochs. So like for 100th epoch, we are getting training of around 80%. So here we can see that we have for 100 epoch, for 19 for 100th epoch, we have a training of it. We have a training accuracy of 80.18%. So then we are saving this model to our model.h5 file, anomaly model.h5 file, and then you are using this file to test our uh, testing videos. So we are using model.h5 files, and we are using this file in our testing file. So before using testing files, we have used the videos of anomaly dataset, like avenue dataset testing videos in our testing. And then we are using test.npy.process. uh, Using this test.npy, we are finding our test.numpy file. Using that test.numpy file, we are testing our model. So to discuss testing, I would like to call Sujay Verma for describing the testing part.
Thank you, Abhishek. Now we'll see how testing is performed in this model. So for testing, we have used the Avenue dataset videos, and testing is performed in this test.py file. We use the load model utility of the Keras models module in order to load our model, which is named model.h5. This mean squared loss function is used to calculate the Euclidean distance between the input frame and the frame which was reconstructed by our encoder decoder model. This threshold value is set to 0.1, which we'll use later in order to declare whether the video is anomalous or not. Here we are loading our model which we had developed. We then load the test numpy videos through this xtest variable. We then reshape it, and if the number of frames is not a multiple of 10, then we take a mod 10 out of it in order to skip a last few frames which are not divisible by 10, so that we can properly feed it to our model. We then reshape our xtest to 227 by 227 by 10 shape. We reshape it, then we extract each bunch out of this xtest, and for each of this bunch we pass it to the model in order to predict the reconstructed frame. And once we have the reconstructed frame, we calculate the loss through the mean squared error loss function which we had defined earlier. So we calculate the loss between the reconstructed frame and the bunch which was originally present in the video. If this loss value is greater than a particular threshold, which is 0.1 in our case, then we declare that the anomalous bunch of frames has been detected, and otherwise we declare that the bunch is normal, and we set the flag as 1 in case of anomalous event, and if it is anomalous, then we print it in the console that it is an anomalous event. Let me just run this file and show you the actual output over our dataset. So as you can see, our code is being run. So there are a couple of bunch normal detections and a couple of abnormal videos detection as well. Let me just run it over the entire dataset. Okay, so this is done. So as we can see from the output, there are some bunch normal videos and some anomalous videos. So for example, let's take this video number 20, which was declared as anomalous. So let me just show you the dataset. So here, this is our testing dataset, and if we see the video number 20 over here, so as we can see that there is an anomaly of this person throwing pamphlets all over the place. So this was declared as an anomalous event because we generally don't observe such a scenario. Let's take an example of a non-anomalous event. So the video number 2, for example, is declared as punch normal. So let's check what actually is there in video number 2. So as we can see that it is a very normal scenario, nothing different or nothing anomalous is happening over here. So this is a normal subway scenario, and that is why it was declared as bunch normal. Okay. Okay. So with this we end our video. Thank you.